Hello students, welcome to my channel. Today I am going to discuss about asymptotic notation in design and analysis of algorithm. In the previous classes I have discussed about space complexity and time complexity. Those are very important, those are related to this topic. If you haven't yet watched, please go and watch. Okay. So here asymptotic notation, it is used to measure the efficiency of algorithm in terms of time complexity and space complexity and other resources. Okay, so the efficiency of algorithm is depends upon time, storage space, and other resources. So the efficiency is measured with the help of asymptotic notation. So it is a Greek word which means not falling together. So this will be understand a bit later. An algorithm may not have same performance for different types of inputs. Okay, so the performance may decrease or increase depends upon the input size. For example, I am performing sorting operation. If the sorting array contains 5 elements, it will take 1 second of time. Assume it will take 1 second of time. If the array contains 10 elements, for sorting it will take 2 seconds of time. So if the array elements are increasing, if the number of inputs are increasing, the performance also decreasing. Okay, so the performance is not same for different types of inputs. So with the increasing in input size, the performance will change. Okay, so the study of change in performance of the algorithm with the change in the order of input size is defined by asymptotic notation. Okay, see this example. In bubble sort, when the input array is already sorted, 90% is already sorted, the time taken by the algorithm is linear. Okay, it will take small amount of time. So this is known as best case. Okay, but when the input array is in reverse condition, that is not in sorted order, the algorithm takes maximum time. So that is known as worst case. Okay. So when the input array is neither sorted or reverse order, then it takes average time. These durations are denoted using asymptotic notation. Best case, average case, worst case. Okay, so these are known as big O notation, big omega notation, big theta notation. These are the three types of asymptotic notations. Okay, big O, big omega, big theta. So big O is known as worst case, big omega is known as best case, big theta is known as average case. Let's see one by one. The first one is big O notation. Okay, so big O notation is a asymptotic notation that measures the performance of algorithm by simply providing orders of growth of function. Okay, so it is used to measure the performance of algorithm. Okay, so this notation provides upper bound is nothing but worst case. Okay, so this notation provides upper bound on a function which will be worst case. It does not consume more than this computing time, so it will consume more time. This notation provides an upper bound on a function which ensures that the function never grows faster than the upper bound. So that is the upper bound. Okay, it does not grow beyond that upper bound. So it gives least upper bound on a function so that the function never grows faster than this upper bound. Okay, and this will also be clear mathematically. If you want to represent mathematically, if f of n is a function, describes the running time of the algorithm. F of n is omega of g of n. If there exists positive constant c and n not such that, so this is the mathematical representation of big omega notation. So first let's see the diagram. Okay, so this is the function of n. This is g of n. Okay, so here big omega notation, sorry, big O notation is always upper bound the function. So it is always upper bound the function. Okay, so the notation provides upper bound on a function. So this is the function. It is always upper bound on a function. F of n is a function. So this is big O notation. So it is always upper bound on a function. So here n naught is a constant. Okay, so The intersection of Fn and Gn is known as N naught N naught. So this N naught is always greater than 0. Okay. So this N naught is always greater than 0, and N is nothing but input. Here x axis is N is nothing but input. Here this y axis is nothing but time. Okay, so if the input is increasing, the time is also increases. Okay, let's see. So 0 less than or equals to f of n. So f of n is always greater than 0. If you observe, f of n is always greater than 0. So that's why 0 less than or equals to f of n, and f of n is less than c of g of n. So here c is a constant. C is also greater than 0. Okay. So 0 less than f of n less than g of n. So this is the mathematical representation of big O notation. N greater than n naught. So always n is greater than n naught. Okay. So n is used to give upper bound on a function. So this represents upper bound on a function. Okay. G of n is upper bound of f of n. If a function is order of n, it is automatically order of n square also. So if it is order of n, it will definitely order of n square as well. Okay. So let's see the example for clear understanding. So I am taking one function. That function 2n plus 3. Okay. So 2n plus 3. G of n is n. So we have to prove g of n is upper bound of f of n. G of n is upper bound of f of n. We have to prove this. Now we have to find is f of n is less than order of g of n. Okay. To check f of n is equals to order of g of n, it must satisfy the given condition. What is that condition? F of n less than or equals to c dot g of n. So this is the condition, right? F of n less than or equals to c of g of n. By using this diagram, we can conclude this one. Okay. Yes, f of n less than c dot g of n. So here c is a constant. First we will replace f of n by, what is the f of n value? 2n plus 3. So that's why 2n plus 3 less than or equals to, what is g of n value? N. So c is a constant, c dot n. So let us assume c value is 1. Okay. So just we are taking constant value as 1. 2n plus 3 less than or equals to 1 dot n. Is it true? No, it is not true. So if we take c value 1 and n value 1, so this becomes 5 and this becomes 1. 5 less than or equals to 1 is false. Next, increase the c value. C value is 2. That is also false. C value is 3. False. C value is 4. False. C value is 5. So in this condition, C value is 5, N value is 1, 2 into 1 plus 3 less than or equals to 5. So 5 less than or equals to 5. This condition is true. Okay. So we are proving f of n less than or equals to order of g of n. When if the constant value is 5, it becomes true. If the constant value, if we take constant value 6, also it will become true. If we take 7 also true, 8 also true, 9 also true. But we have to take the least value. Okay, we have to take the least value. So 5, 6, 7, 8, 9. Among this, 5 is the least value. So we have to take least value. So for n is equals to 1, the above condition is true. If n equals to 2, if we take n equals to 2 also, this condition becomes true. So by this, we are proving f of n less than or equals to order of g of n. Okay. So this is big O notation. So it is represented with O. Okay. So the next one is big omega notation. So it is the reverse of big O notation. Okay. So this is, it shows the best case. Okay. It will take less amount of time than the function. Okay. So it is defined as lower bound, and lower bound on an algorithm is the least amount of time required. So it will take least amount of time for the algorithm. Okay. Just like O notation, big O notation provides an asymptotic upper bound, omega notation provide asymptotic lower bound. Okay, so by seeing this we can understand. So this is the function. G of n is always less than the function. G of n is always less than the function. So we can say f of n greater than or equals to c of g of n. By using this diagram we can say f of c g of n less than f of n, or f of n greater than or equals to c g of n. Okay, so 0 less than or equals to c g of n, less than or equals to f of n, where n greater than n naught. Always input value is greater than n naught. Okay, so n is used to given the lower bound. So this is n, it is used to given the lower bound of a function on a function. So if a function n square is, if a function is omega of n square, it is automatically omega of n as well. So it is reverse. Okay, so let's see the example program. Same example. Here f of n is 2n plus 3 and g of n is n. So we have to show f of n greater than or equals to c g of n. So in big O notation, f of n less than or equals to c g of n. But here in omega, f of n greater than or equals to c dot g of n. So let's see, if we take c value is equals to 1 and n value is equals to 1. So this condition is true. So see this, if we take c value is 1 and n value is 1, so 2 plus 3 is 5. 5 greater than or equals to 1. Is it true? Yes, definitely it is true. So by this we can conclude f of n greater than or equals to c dot g of n. Okay. So and the last one is big theta notation. So it is average case, not best case, not worst case. It is average case. It is defined as tightest bound, and tightest bound is the best of all worst case times and that the algorithm can take. Okay, so it is represented. See this example. So c1 g of n less than or equals to f of n less than or equals to c2 g of n. So here we are taking 2. So it is average. Okay, so c1 g of n is less than f of n is less than c2 g of n. By seeing these diagram we can write this. See this one, f of n less than or equals to c1 g of n for n greater than, yes, n greater than or equals to n naught. See this one, c2 g of n is less than f of n less than c1 g of n. Okay, yes. The equation simply means there exists a positive constant C1, C2. So in big theta notation, we are taking two constant values C1 and C2 such that f of n is a sandwich between C2 and C1. So we have to prove that. Just wait a second. Here f of n greater than or equals to C of n. So here C1, yes. So this is also true. Okay. See this example. So we are taking f of n is equals to 2n plus 1, g of n is equals to n. So we have to prove this one. C1 g1, C1 g of 1 less than or equals to f of 1 less than or equals to C2 g of n. So C1 should be less than f of n and C1 has to be 1, whereas C2 g of n should be greater than f of n. So C2 is equals to 5. So just we are taking constant value. So I am taking C1 as 1, C2 as 5. You can take any values also. Okay. But this condition should be true. C1 value is 1, C2 value is 5. And n value is 1. So we are taking n value is 1. So implement this one. Sorry, here I took C1 value is 2, C2 value is 3, n value is 1. So implement in this one, C1 value is 2 into 1 less than or equals to 2 into 1 into 1, sorry, 1 plus 1 less than or equals to 3 into 1. Why? Because C2 value is 3. So 2 less than or equals to 3 less than or equals to 3. So this condition is true. By this we are concluding C1 dot g of n less than or equals to f of n less than or equals to C2 g of n. You can try with different constant values also by using different inputs also. Okay. So I hope it is clear. Big O notation, big omega notation, and big theta notation. If you have any doubts regarding to this video, please comment me in the comment section. For more videos, please do subscribe my channel. Thank you.